Welcome to my world. Another day, another time. This time around, we're going on the topic that is also very interesting. It has to do with measurement, it has to do with science, it has to do with application of findings, applications of scientific discovery. We know one thing clear, that light is important. But what we don't know is that light brings color. Without light, you cannot see any color. Light brings visibility. That is also very clear. It is all these discovery that is now used in the laboratory to measure the intensities, and that is where the content of this video is heading to, so that you can understand how we are able to apply the knowledge acquired from scientific discovery to really help in diagnosis of a confirmatory diagnosis of one ailment or the other. The aspect of wavelength, how come wavelength and frequency will be well discussed as we continue in this journey of acquiring knowledge. If you like my channel, just subscribe, press the like button, and always you'll be informed. Let's move on to the real proper study. Now let's look at the outline. The outline is as follows. Definition of keywords. The first, understanding of light by Newton and co-workers. The second, understanding of light by Albert Einstein and other researchers, great researchers like him. Then the application in light microscopy to study microbes in microbiology, histology, anatomy, and other study subjects. Application of spectroscopy, that is when we are talking of wavelength, in hematology, clinical chemistry, endocrinology, etc. And then the last part is where the latest research in medical laboratory measurement. The definition. The definitions, we start by looking at light. Light could be defined as the natural agent that stimulates sight and makes things visible. The nature of light is both a wave and a particle. The wave-particle duality. This is now known. Those days, in the early 16th century to the 17th, up to the 17th century, the time of Sir Isaac Newton, it was not so known. So it's generally believed that light is a stream of particles and stuff like that, but that aspect of wave was unknown. So the two aspects of both that stream and the wave has become very known and is now in use. From wave, we define wavelength. That is, after finding that light is also wave in a way, so you could talk of wavelength as the distance between two wave crests, and it will be the same even if you use the chalk. The wave nature of light could explain that light travels in a straight line, as well as that is an electromagnetic wavelength of speed of 3 times that to pass per second, and it could also travel through vacuum. So if it travels through vacuum, it's it's just straight, no reflection. This is where you now find the duality being experimented. The light strikes, you can see the wave nature. It forms that circle, just like when you drop something in water, and water moves towards a crest, a stone or anything, it now forms this concentric circles. This is the wave that we are talking about, and the duality is also talking of this string that goes, and the optical screen sees it, and that's the front view. The number of vibrations that pass over given spot, that's frequency, in 1 second, and it is measured in circles. That is when you're talking of the wavelength per second. That is when you want to define frequency. Another way I've simplified it is to put it this way. The period of Isaac Newton and the period of Albert Einstein, they didn't happen at the same time, but the challenges of Isaac Newton was taken up by the Albert Einstein scientists, and now we have data scientists even going on to talk more about life itself, and probably not real and stuff like that. So we are still on. Science is a continuum. Light as a particle, that is the theory at that period. So it travels, light as was a motion of particles, like also in straight line. So I drew the straight line so that you can understand it like that. So when it touches its refraction, that they came to know later. And the clear light was composed of 7 visible colors. That was known during that period, even though it was not so proven as 7, but it was suspected to be 7 because of the rainbows and also the key notes of music that Isaac Newton, so highly respected scientist, so whatever he says holds. And then came the light as a wave theory, which holds now. So you now see the wave, just like I told you when water, a circle, it forms this wave. These are the wavelengths. And when you want to measure wavelength, it is from that point of up to this point. That's one wavelength. And if you have to even do it like this, where it's like a valley, it's also the same one wavelength. But what you discover is that this wavelength starts from very little and it expands to, if you attach this to it, continues like that. But these are the various shape, the various level of property, the behavior of light. It could be behaving as starting from gamma rays, that is also being used. X-rays, is used to these. They don't really penetrate all this at this level, though the frequency is very high at this level. You can imagine the drop that you can count here. The peak, these are the peak, and this is the drop. If you count the number of peaks here, you will find that it's almost double this. So the frequency is very high at the lower wavelengths, but the penetration too, that is the problem. So it's always at the surface. The X-ray would take the picture you want to take of those areas that cannot penetrate, and you see it in a film. The ultraviolet ray radiation is also used for the microwave that we have, and then you now have the visible lights that will come as violet, indigo, blue, green, yellow, orange, and red. So it's so explanatory. And then this explains that the duality of that light can behave as electromagnetic wave, whereas the particle nature of light states that light consists of particles called photons. Now let's go to this next stage. First, understanding of light. With that understanding, we use the Newton model of light proposes that propagation of light is caused by the rectilinear motion of light particles, which we term light corpuscles, moving in a straight line. These light particles travel at a finite speed, and their interaction with the external environment, for example, it's at a finite speed, and so they interact with themselves. Let's say, example, rigid surface, wall, and human obey Newtonian physics. These are facts. Newton thought that light was a motion, yes, like I said, in straight line, and that was what was used around that period, you can imagine that the microscope existed before you start talking of colorimeters and stuff like that, because at the level of colorimeter we are now talking of wavelength. Right now, at this level, we are not talking of wavelength, we are just talking of that refraction property. This, when it moves from, light moves from one medium to the other, it's bent. That bending is what was just being, and this is Isaac Newton himself. And the second understanding of light, you now bring Albert Einstein, who is also a very great scientist, if not greater than Sir Isaac Newton, because he more or less helped him to prove the interference that they were not able to prove, the interference of light, that light interferes with each other because of that wave that they couldn't accept, or probably they couldn't prove. So Max Planck was the first to really come with that. A renowned German scientist found in 19 that a particular type of metals ejected free electrons in contact with light. This experiment duly dealt with the photoelectric effects of light. So they now started thinking of light as probably as electrons. So that is where the word photon came about. It was Sir Isaac Newton that helped create that word photon anyway. This is the picture of Max Planck. And later on, Albert Einstein followed up on this experiment and discovered the particle nature of light, which I just mentioned, the photon aspect. That's Isaac Newton in that picture, a very popular picture. The application of all these ideas, let's first of all use the idea of Newton, which brought about the microscope. So let's see. The property of light, according to Isaac Newton, move together in a straight line, consisting of a stream of particles. The angle of incidence, that is where microscope came in, and refraction, that is that bending, which are created when light moves from one transparent medium to another. This was discovered by and stated by Snell. Though I don't have this picture. So this you can easily see. So with sunlight, you can see sunlight eating the water, and these are the fish. Or it's not even just one fish we are talking about now. But the light of incident, when it gets to this point, you find it bending to reach the high, because this medium is different from the air medium. The water medium is different from the air medium. So light here reaches the air a little later and speed up, because light, this frequency is what we've mentioned about, is in the speed of that wavelength. So you can then see bending, and that is what is used in the first idea of compound microscope. This is it. So you can see the monocular. This is where you probably put your eye. I was not born there, so I wouldn't go around the 30 before. And this is the mirror that collects the light and transfer. That's the light comes and goes straight up here. Whatever they want to examine is there, and the eye will now see it. Hello. So microscope, 18th century. This is the 18th century drawing. This drawing shows a compound microscope used in 18th century France. First developed in the late 16th century, compound microscope used two or more sets of lenses to achieve high magnification. So you can understand why it is called compound, because of two or more lenses used. Then this is a very modern one of it. You use sunlight, you collect the sunlight and do exactly what that pictures, the first one we saw. Now this is the closer we have gotten. You have binocular. So also it's electrical. They plug it and the light comes with the light source passes through. This is the stage, and everything will be labeled here. You can see this is labeled so that anybody, the stage, will use fine adjustment and so on to get the best of the picture. Now to application of spectroscopy in hematology and chemistry and endocrinology and any other field. The wave theory of light came into existence through Planck and as explained earlier. The other property of light, reflection, which Isaac Newton get to explain light interference, was what they were able to do. We could now measure wavelength and frequency, which was never thought of being in existence during those periods. So these wavelength and frequencies are now what we use in our colorimeter, spectrophotometer, and so on and so forth. So using that, you can see that the ultraviolet light is of a smaller wavelength but high frequency. The visible blue, which is under visible light, these are invisible where you don't see. These are dark areas you don't see. Even the infrared is dark. But this area, this region now tells you it starts from 400 to 700 and the frequency are lower than that. The infrared has chromatic light, monochromatic light. This is the polychromatic. Now, when it comes, this is the lens. It allows you to converge here. The convergence here is what now with this monochrome filter, it allows only the red light, the other frequency, to pass through. And that is what now meet the cuvette and read on the forces which will now come out in the meter. You can see the meter reading. So this is exactly what is done there. Now this is the example of the colorimeter. This is the formula according to Albert's law. A for absorbance, E for absorbability, E for length, and C for concentration. When you get the absorbance of the test, you put it on the absorbance of the standard and multiply by 100, especially for glucose estimation using draft scale solution. This is the other major machine that is used, the six-mens machine, and it also uses the wavelengths that will allow for this absolute reading. So the assessments do complete blood counts, WBC, RBC, hemoglobin, and every other thing up to the nutrient. These are advanced, so you can expect it's just the blood that you put. And this is for the chemistry analysis, COBAS C111. So it will do the following test: biochemistry, even up to the sodium, potassium. These are ions. It will estimate them, though they have no color, but you find them in red. So the bilirubin, and then that's right. So it performs so many tests. The latest is the ion selective electrodes. You can see the electrodes that are used to do the potentiometry calculations. And this is the ISA photometer right there. Now the latest idea in medical laboratory measurements, you can talk of microscopy photometry, scanning the aperture and the SIAM. The electromagnet uses electrons to emit an object. Yes, electrons have a much smaller wavelength. So you are still talking of wavelength than light. So they can resolve much smaller structure. This smaller wavelength of visible light is about 400 Armstrong, that is in meter. The wavelength of this is 50 trillionth of a meter. So this is the electron microscope itself. Thank you.